And welcome back. So taking a look at this your turn, it's that cos of theta. So if I'm looking for that non-permissible value, it happens when cos of theta is equal to 0. And when does that happen? Well, when my x values are 0. So I think it's at that one and then that spot over there. So I'm going to say the non-permissible values are when theta is equal to pi over 2 or 3 pi over 2, or another way to state your answer is that theta cannot be equal to either of those values. So just to get the big idea again, this is an identity, which means that it's kind of like a definition. It's like always true. It's always true except for occasions where you would get a division by 0 error, and we call those values that produce a division by 0 error non-permissible values. Okay, so let's take a look at the next page. There's the question there. It says, and I think you may remember this from chapter 5, is 1/2 comma root 3 over 2 on the unit circle. I'm going to change the way this question is asked, and I'm going to say verify that blank blank is on the unit circle, and I'll make that a request rather than a question. Okay, so if we do verify, there's more than one way to verify, but a good way to do it is to draw one of these T's and then to write what's on the left and what's on the right and see if it's equal. And so the way we've done this, we've said, is x squared plus y squared equal to 1? So my left hand side will be x squared plus y squared, and the right hand side will be 1. And so if I put this in here, I'll get 1/2 squared plus root 3 over 2 all squared. So I get 1 over 4 plus 3 over 4. So that's 1 equals 1. So left hand side equals right hand side. So I say yes, it's true, it is on the unit circle. So like, how does that work? Why is that true? This is my x value. This is my y value. And so we know that sine, I often say sine is the y value on the unit circle, but I should be kind of careful. I should say that sine is equal to y over r, and cos is equal to x over r. And on the unit circle, r is equal to 1. So my shorthand method is often saying sine is equal to y and cos is equal to x. But really I'm just talking about when it's on the unit circle. I was just going to remind ourselves about that. So, so we also know that the equation of the unit circle is this. So that's what we just used. So if we substitute here our x squared plus y squared, and on the unit circle, x is going to be equal to, I guess the direction, the order kind of changes here. So I'm trying to introduce some of the identities that are on our formula sheet. So if I just pop over here looking at our formula sheet, here is this identity that they give us, sine squared plus cos squared equals 1. And what I want to emphasize is, where does that come from? It comes from this x squared plus y squared equals 1, which really comes from Pythagoras. So that's how that is derived, I guess is the right word. You don't have to go through and tell me why sine squared plus cos squared is equal to 1, but it's something that you're going to be using quite a bit. So there's two other forms of this equation that's pretty handy. So if I take this identity, sine squared theta plus cos squared theta equals 1, and I subtract sine squared theta from both sides, then I would get this one right here, cos squared theta equals 1 minus. And I just want to take a look at that, 1 minus sine squared. And I can 1 minus sine squared theta. Now, I want you to recognize that this is actually a difference of squares. So remember way back in the day when we would say a plus b times a minus b, and if we multiplied that out, we would end up getting a squared minus b squared. I picked different letters than x and y just to not confuse us. So if we multiply, we're going this way. But if we factor, we can go like that. So this is factoring. So this is actually, so in grade 11, we spent a lot of time trying to recognize these when we have two terms that are squares, and if it's a subtraction in between, we call that difference of squares. So we can factor it. Now, 1 minus sine squared theta is a difference of squares. 1 is a square of 1. sine squared theta is a square of sine theta. So I can actually factor this, and I can say this would be the same thing as, you know what, I need a little bit of room here, so let's see if I can move it over. There we go. Okay, so this would be, if I factor this, using that same pattern, it's going to be 1 plus sine theta times 1 minus sine theta. So that's why over here this is a very useful pattern, because we can go and we can factor it like that, of 1 plus sine theta and 1 minus sine theta. Same thing with this one. If we take the original identity here, sine squared theta plus cos squared theta equals 1, and we subtract cos squared theta minus from both sides, we get this form of that same identity, and that 1 minus cos squared theta is a difference of squares, which you can factor again. The next one on our formula sheet here, if I'm looking at the formula sheet, is this tan squared theta plus 1, and then the next one 1 plus. These two here, I'll just show you where we got them. And again, you don't have to be able to do this, but I'm just showing you how it works. If we take the first identity, that's that one over there, and we divide both sides by cos squared theta, and when we divide both sides, we got to divide all the terms on the left. So each of those terms separated by the plus symbol, by cos squared theta, that's how we get this identity. And likewise, if we divide by sine squared, that's how we get that identity. And just a reminder that these identities are only true when these functions are squared. So sine squared theta plus cos squared theta equals 1, but sine theta plus cos theta is not equal 1. And just a reminder, it's like sine theta times sine theta equals sine squared theta. If it was up to me, we would probably be doing, I kind of like this better because that kind of makes more sense. But this 2 right here means it's not like we're doing the sine of theta. It means we're doing sine theta and then squaring it. So that's what that means. Just like x squared is x with raised 2, here's sine theta squared. We put that raised 2 by the sine word. Okay, here's example number 2. It says, verify that this equation is equal to sine x is true for x equals 60 degrees. Okay, so if it's a verify, again, I'm gonna make my t-chart here, see how much room I have on the page. So I'm gonna make my t-chart like that, and I'm gonna put on the left-hand side the secant x all over tan x plus cotan x, and on the right hand side I'm going to put sine x. And then I'm going to try to simplify the left hand side so that the left hand side is equal to the right hand side. But actually I need to do this for 60 degrees. So what I can do is say, okay, I'm going to test whether this is true at 60 degrees. So I'm going to put 60 degrees here, 60 degrees, 60 degrees. So I'm going to find out whether or not the left-hand side is equal to the right-hand side when x equals 60 degrees. Notice that's the only test I'm doing. I'm not testing for other degrees at this point. I'm just checking for 60 degrees. Okay, so maybe beforehand what I'm going to do is just do a little bit of prep work and say, okay, so the sine of 60 degrees, and there's a reminder that I'm in school. Sine of 60 degrees, the cos of 60 degrees, we're going to try to figure out. And then we're going to try to figure out the tan of 60 degrees. And then we'll do the inverse one. So the inverse of sine is cosecant. Here, I'm moving a little bit. The inverse of sine is cosecant 60 degrees. The inverse of cos is the sine. Oh, sorry. Is secant, SEC of 60 degrees, and I'm saying inverse, but technically it's the reciprocal of tan is cotan. Okay, let's see if we can figure these things out. So at 60 degrees, seems rare that we're not doing this in radians again, so it's up over here. So my x value is 1/2. And my y value is √3/2. So the sine is root 3 over 2. And the cosine is 1 over 2. And my tan is going to be, well, it's root 3 over 2 over 1 over 2. So I can simplify that. If one way I can simplify that is, instead of dividing by a half, I can multiply by the reciprocal. So I'm just going to erase this, and instead of saying divided by a half, I'm going to multiply by the reciprocal. And then you can see how my 2's, I have a 2 in the numerator and the 2 in the denominator, so I can cancel that out. And so I've got, this is equal to root 3. And perhaps this was one that you had remembered about in the past. Okay, so now cosecant is the reciprocal of that. And so instead of root 3 over 2, it's 2 over root 3. The secant, instead of a half, is going to be the reciprocal of a half, which is 2. And cotan is the reciprocal of root 3, so that's 1 over root 3. Whew, now I've done all that work. So now it makes things a little bit easier over here. Switching over back to blue. So secant of 60 degrees is 2. So I'm going to say 2 all over. The tan of 60 degrees is root 3 plus the cotan of 60 degrees is 1 over root 3. And looking on the right-hand side, the sine of 60 degrees is root 3 over 2. Okay, so I've got some fraction work here to do to find out whether or not the left-hand side is equal to the right-hand side. So the first part I'm going to do is look at the bottom of my complex fraction. I'm going to combine these two fractions. So to add and subtract fractions, the denominators have to be the same. So first of all, I'm going to make that have a denominator of 1. The lowest common denominator for the O's is going to be root 3. So what I'm going to do is on this one over here, I'm going to multiply by root 3 over root 3. So what does that give me? I'm going to rewrite this. I'm going to get 2 all over. This is root 3 times root 3, so that's 3 over root 3 plus 1 over root 3. Now I have two fractions in that big denominator which have the same denominator. So now I'm going to get 2 all over 3 plus 1 is 4 over root 3. Now I'm going to use the old dividing as the same thing as multiplying by the reciprocal. So I'm going to say 2 times root 3 over 4. And now I can say, hey, I've got a common factor of 2. So I'm going to divide the top and the bottom by 2. So I get a 2 here and a 1 here. And I get root 3 over 2. And that's the same as my other side, which was root 3 over 2. So that's a lot of work to get this fraction. In this chapter, we got to take our time and deal with the complex fractions and take care of these things. So that's part of what this unit on identities is going to be, is dealing with these complex fractions, remembering again about having lowest common denominator, remembering how to divide by a fraction is the same thing as multiplying by the reciprocal. Part C says, state the non-permissible values of the above identity over the interval. Okay, so if I look back again here, I think what's in the denominator. Okay, so the tan of x, tan, remember, is sine over cos, and cotan is cos over sine. Oh, I think I went too far here. We'll get back. So for this entire thing, I'll just rewrite this part. I had secant x over tan of x plus cotan of x. Remember what I said we should unpack things. That's the same thing as 1 over the cos of x all over the sine of x over the cos of x plus the cos of x over the sine of x. Let's look at all those denominators. Well, I've got a denominator here of cos, here's another cos, and here's a sine. So really it's whenever the non-permissible values is whenever sine of x is equal to 0, or whenever the cos of x is equal to 0. So looking at the unit circle, it'd be all 4 of those points here, because here's where the y value or sine is 0 here, and cos is 0 there and there. So my non-permissible values is when x is 0, pi over 2, pi, and 3 pi over 4. We've seen that list a few times. Okay. So example number 3, there's 3 examples, and what my suggestion is maybe watch me do them once, and then maybe don't write it all down, and then try on your own, and then like see if you can do it, and then check the video. You know, you've got your own methods maybe of learning from watching videos, but if it's just always you watching me do it, then it gives you the illusion that you're learning sometimes. So I really encourage you to figure out some way to try these on your own. Maybe you want to just watch me do them once, or you could write them down with me and then take out a blank piece of paper and cover the answer and try it again. But in any case, let's try these. The first one says the tan. Oh, we're supposed to simplify the following expressions. So what does simplify mean? If say at the end of my answer is the sine of theta, that's very simple, right? Try to get it down, or if it is just says the number 1. So try to get it down so it has the fewest terms possible. So what I'm going to do is, again, like I said before, unpack it. So whenever I see a tan, I'm going to change that to sine over cos. So let's do that. Here we got sine theta over cos theta times cos theta all over. Secant is the same thing as 1 over cos theta times cotan is cos theta over sine theta. Okay, so now a word about when you can and when you can't cancel things. So I'm looking here. Cos is the same thing as cos over 1. So I can cross those two out, because really what I'm doing is I'm dividing both the numerator and the denominator of that upper fraction by cos. So that's good. So if I had, say, like x times y over y, I can cancel those out. But if I had x plus y over y, I can't cancel that out. And the reason is that these are two different terms. Now, terms are separated by pluses and minuses. So those are two different terms. If I wanted to divide the top and the bottom by y here, I would have to divide each of the terms in the numerator by y. So if I did that, I would get, x over y plus 1 all over 1. Like once I've divided this by y, and that by y. So which is different, isn't it, than just canceling it out. So again, you can divide both the numerator and denominator by cos theta or anything else, but then you need to divide each of the terms by cos theta, and terms are separated by pluses and minuses. I hope that helps you. So in the denominator, again, I see a cos theta up here and a cos theta down there, and I can cancel. So what I'm doing is I'm dividing cos theta from both the numerator and the denominator in that denominator. Okay, so what am I left with? I get here sine theta over 1, so I don't have to write that part, over 1 minus sine theta. So I'm almost done here. So now I could multiply by the reciprocal. So I'm going to get sine theta times sine theta over 1. So I'm going to get sine squared theta. Put a little box around it to say I'm done. I'm just going to stop this video now, so just to chunk it so you don't get intimidated by the lengths of the videos, and I'm just going to carry on the next video.